Hello everyone. Now I'm trying to show you how to solve the exercise 4, which is about the effect of a mutation. In our case we will see two examples of a structure which is the transcription factor p53, and we are studying two example mutations in order to see how FoldX is dealing with the prediction in that situation, how you can also use it for specific cases to see interactions between two different molecules, for instance. So P53 in our example, it's from a structure from the internet, which we have prepared a little bit in upfront because the crystal structure has been solved as a tetrameric complex, and we will only look into one of the monomers, in fact. So this means that I don't load it from the internet, but I load it from Yazara-Zine. So it's 2ACO, and luckily my colleague who has prepared that some time ago had already chosen a nice representation where you see here the protein, and on top the DNA bound to this protein with a classical double helix structure. So just to see here, in fact, so we have molecule G, H and C in fact is the protein, as you see, and then we have the two DNA part. Okay. Now the first thing we would do is, before we study the mutations, is to minimize the structure, and this you do by choosing the FoldX module repair object. So we go to Analyze FoldX, and then you see here the long list of options you can choose within FoldX. This is the version 5, and I have, of course, beforehand configured the plugin so that it knows where the FoldX executable is residing. So the first step would be repair object. This would start the energy minimization, and I will do this now, but will then also stop the recording for a second and resume it afterwards, because this takes a little bit and it's just boring to watch. So you see that FoldX is opening and is giving you some additional information on that it has been started, and now it's passing over all the amino acids and also the DNA structural elements, the bases and the backbone, and will minimize the structure. So this can take roughly 5 minutes, so this is why I will stop the recording here. After the minimization has succeeded, you will see that in the Yazara interface there is a second object which is called repair object 1. So I can switch this visibility off here, for instance, and on again, and in this case there's no structure shown. So we just have to be aware that there are now two objects, which can be sometimes a little bit distracting. So we'll switch this off first so that we don't see any atoms from the first object, only the representation effect. And the structure, the amino acid, sorry, we would like to mutate is alanine 159. So the important thing is that we identify where this is. So I will first open this repair object and do some very short visualizations. So I do show atoms, molecule, and then from the second object, which is the minimized version, GH. Okay, so now we see the same view than before for 2ACO for the crystal structure. So the DNA part is visualized. And I also want to visualize the alanine 159. It's here, so I'll click here on this in our overview. Okay, and you will see that alanine here has been shown. It's very small. Yeah. So here it is, in fact. Let me do it like this. So here's the side chain with one carbon atom and of course 3 hydrogens on it. So in order to go further, we will mutate this residue. So I'll mark it as it's done here and then go to Analyze, Foldix, Mutate Residue. And now again here we have to be careful that we select the right molecule in the chain C, which is asparagine alanine 159. So this is the second molecule. Okay. We don't run Foldix repair, in fact, and we also don't calculate an interaction energy because in our case the amino acid is in the protein, so I want to calculate the stability change. And I indicate, and this is just really for the example, that we would mutate it to a tryptophan, which is, as you know, of course, a very big side chain, has a very big side chain. Okay. We asked to move neighbors because I suppose that you also realize if you have such a big side chain compared to alanine that this might be necessary. And we don't expect hydrogen bonds in this case to be disrupted because it's a hydrophobic amino acid, alanine as well, and tryptophan for sure. So we show the van der Waals clashes in the wild type and the mutant. In this dialog we don't change any options, so this is the default options. And then Foldix will also start running. So as you see, it will open the calculation window, and this takes a little bit. We'll calculate the initial start energy of the current complex, and then starting build model to point mutate the amino acid. In this case, alanine from chain C 159 to tryptophan. Then it does a very short superposition step, and then it's already done, as you see here. Okay, so I will shortly collapse this. So now you see that we have a third model here, which is kind of superposed again. So now we have to look that we find something which you can see. So as you remember, here has been the alanine, and you see now the tryptophan is present, and as you see, it's really a big residue, and the red residues which are shown here and also like flickering a little bit, so those are now of course in big sterical hindrance, and this will probably also, as we will see in a second, result in a very unfavorable situation, in fact. So let's see what Foldix has calculated, whether this mutation would be stabilizing or destabilizing. So I open with a space, typing 2 times this window to have it largest. So again here, if I scroll up a little bit, I hope I can do this. Yes, I can do this. So this is Control. I press the Control key and then arrow up. So then I can move a little bit in this interface. So let's see. So here is FoldX build model running. And once it's finished, it is superposing the structures with the Mustang method, as we have done it before as well. So a sequence alignment, which in this case, of course, is trivial since it should be identical. Only one position is different. So you see it here indeed. The overall superposition of the backbone results in 0 angstrom RMSD, which is kind of logical because only the sidechain basically has been moved. 195 aligned residues, and of course only one is different. So we have 99.5 sequence identity. And then we scroll a little bit down in order to see the output from the FoldX plugin. So the object here, which has been mutated, so AC159W, is now object 2.1 in this plugin, so that's kind of a little bit disturbing. This means it's the 86 residue, so that's kind of unfortunate here that it doesn't say the same, but in this case it's exactly what we have been looking at. So it's alanine 159, but it's the 86 index, so to say, the 86 amino acid. So this is kind of a little bit disturbing, but I will check how we can change that in a later version. So this is basically the line you have to look at. The total energy is 29.25 kilocal per mole, and this is of course positive, and as we said before, this means clearly very obviously a destabilizing mutation. And as said before, this is also indicated, you see it here, so it's really super dense there, so that can't be possible at all. And also the red side chains from the other, also usually big, like here, phenylalanine. Or a tyrosine here in the back, so these are all very big side chains, and then you would put there another tryptophan, so also very big side chain. This cannot work. Okay, so that was the first mutation we would like to study. And for the second to run, I will just wipe this situation and reload the energy minimized version of 2ACO. So that we start from the same situation, 2ACO, and the repaired object effect. So I will do this again. View show molecule, and then the 2 side chains, G and H. Okay. Good. So now I wanted to show you another option which you can use FoldX for, which is to see whether there is a change in the interaction energy between 2 different parties, in this case the DNA and the protein part. And for this we would like to use an amino acid which is, of course, from the chain C. I just have to scroll down and I find it, which is arginine 273. So I'll visualize it. So, and as you see immediately, it is very close, this arginine. So here you see the moiety on the end of the side chain, charged moiety, positively charged moiety, which is in close proximity with the phosphate, indeed, side chains from the bases. So this is, of course, most probably a very favorable interaction situation. And in this case, we just do this mutation again and replace this charged amino acid by an alanine. So, of course, that's also a very extreme situation, but just for the demonstration of Foldix and how you can use it. Good. So we go to Foldix via the Analyze menu, and then here again say mutate residue. From the second object, we take asparagine 273. And in this case, of course, we want to calculate the interaction energy change, because it's two different molecules we are looking at. And the mutation pardon me, so there's something not going wrong here, not going correct. So Foldix mutate residue, calculate stability energy, yes. And then we mutated to alanine. Okay. So here in this case, if you think that the alanine is here, so you know already that this will be the position, so there won't be much to move neighbors. So this we can uncheck. And of course, in this case, we anticipate that there will be a lot of disruption and hydrogen bonds not necessarily formed, but most logically disrupted. So I will check this box. And here again, we don't change anything. And then we wait for Foldix to complete. So you see this goes very fast. And in our first view, of course, you see here again the arginine with the hydrogen bonds to this side chain of the same protein, P53, but also, of course, to this phosphate group here. So, and of course, we will hopefully see that once you have the alanine, then this shouldn't be there anymore. So you see, if I visualize this repaired object, there is only the alanine here, and of course there's no interaction. If we switch it on, again you see that here are the hydrogen bonding patterns. So there's clearly a charge interaction with a lot of partners. Good, let's open the command window. So I will also move a little bit up. To find it again here. So again, we have the similar situation that the mutation, of course, resulted in a very close superposition, an ideal situation, with only one amino acid difference. And as Foldix in the mutate residue setup calculates this total interaction energy, it's also favorable. So that's logical. but of course not necessarily what we wanted to see. So I just have to look whether I see the other examples as well. So it's not there. Okay. Good. So then we will do it by hand. Just trying to find out. So this is interaction energy we would like to calculate with the chain G effect. So let's see how we can do this from the repaired object. Okay, let's have a look. So in the Analyze menu, of course, we have the fold X again, and there's also a option which is called Interaction Energy of Molecules. I will use this one for the second molecule. So we have to select here between chain G and chain C. Let's see. Pardon me, so mistake. Analyze, fold X, interaction energy. The first molecule in the range of the second object is G, and the second is C. So fold X will start. So in fact, what it has been calculating is the interaction energy is -6 kilocalorie per mole, which is a favorable interaction. So this is just something we will note down. And we do the same exercise for the mutated situation. So analyze, fold X, interaction energy. And now we take the same combination of object 3. So G with C.